Hello, and welcome to the Curiox Biosystems webinar. We're happy that you joined us. We will have two speakers today. First, Dr. Prabhakar Putheti of the Rogosin Institute and Weill Cornell Medicine, and Dr. Charles Martin, Director of Marketing for Curiox Biosystems. The presentation will take approximately 30 minutes, followed by a question and answer session. Please type your questions in the question box as we go along, and we will address them at the end of the presentation. The webinar will be recorded and will be available at www.curiox.com. Now, without further ado, Dr. Charles Martin.
All right, thanks, Sheila, and welcome to our webinar, everybody. We're excited to share some customer results with you, and then Prabhakar will follow me after my short presentation, and we'll share experience and data from his cross-matching work. So many who perform cross-matching will immediately see the value of process improvement, better quantitation, and reproducibility that we believe drop array can deliver. So I'll use the term drop array and DA cell kind of interchangeably during this presentation. Much has been done to standardize and improve flow cytometry over the past half a century through instrument improvements and software automation for analysis. But the area that has received the least attention for standardization is sample preparation. And one of the main reasons for that is it's very difficult to standardize centrifugation and flicking and dumping and aspiration. And drop array can enable standardization to sample preparation by eliminating much of the human variability in those techniques of aspiration, flicking, and other aspects. So it's been pointed out over the past few years by quite a few prominent scientists that reproducibility can be an issue in science, and washing of cells by automation methods is key to generating reproducible data, especially in flow cytometry and also cross-matching assays using flow cytometry. So you've seen this kind of reproducibility crisis issue show up in Science and Nature and other publications quite a bit over the past 5 to 7 years. So we've introduced the DA cell washer, and the DA is for drop array, and it's shown on the left of this slide, to wash cells in a 96 well format using our proprietary plates that allow a laminar flow. And this allows us to remove user variation that occurs during centrifugation and the aspiration or flicking of plates. And we're working on a next generation that's kind of visualized in a prototype version on the right panel that will be a fully automated workstation that would include addition of reagents, incubation steps, etc. Essentially all the steps you need in surface staining and or intracellular staining protocols from beginning to end. So here, this slide's a comparison of what happens in centrifugation and what the benefits are of the drop array cell washer. And the drop array cell washer is positioned to minimize all of the challenges listed under the centrifugation of cells. And the one that's not mentioned there is automation. And it's really challenging to automate a centrifugation step with a robotic system. There's just a lot of moving parts in a centrifuge. So in a conventional wash process, scientists typically use a centrifuge and a multi-channel pipette. And then if you do a wash of, say, 2 centrifugations, that's going to take maybe 15 to 20 minutes, depending on what your particular protocol is. Whereas the DA cell takes care of the entire wash process automatically in 2 to 3 minutes without centrifugation. And also without centrifugation, cells do not experience any external forces or stress. So in this slide, I'm going to show a short movie clip of how the DA cell washer works. And on the left panel here, this is an actual plate. And we've got, there's 2 wells that look green, and they've got green polystyrene beads in them. And then the 2 wells to the left have food coloring in them, which stand in this case, for the labeled antibodies. Let me start the video. And the fluorescent beads will settle to the bottom of the well just like cells would. So they have about the same density. So then the user places the plate in the washer and hits the start button. The head has 192 nozzles total, so 2 nozzles per well, one for dispensing and then one for aspiration in each well. In this case, we've lifted the cover so you can see what's going on inside the washer. And during the 2-minute operation, it performs 7 cycles each of dispensing and aspiration. So that would be equivalent to a couple of washes with a centrifuge. So when the wash is complete, the plate comes out, and in the picture you can see that the food coloring now is completely gone, and it looks just like the other wells in the plate, which just contain buffer. But yet the green beads are still there, which represent the cells are retained on the plate. And now you may wonder yourself, how come the ink was washed away while the beads were retained, or in the case of an actual assay, cells? And so to clarify, the beads are not attached to the plate by any interactions, just as the cells aren't. They're just held there by gravity. And I'll show you in the next slide how this works with a little cartoon. So the top row is what's going on in a tube or microplate in a centrifuge, and then the bottom row is the DA cell washing method. So the retention of the beads or cells, in the case of an actual assay, it's based on well-characterized forces of gravity and then laminar flow, which are very well-known and characterized forces. The secret is that we use each force on an almost flat, wall-less plate. So there's just a very small depression in the plate, and that's where the cells are allowed to settle. And at the bottom, you can see the working mechanism of the cell washing by DA cell. The cells are mixed with your antibody cocktail, and then they're allowed to settle on the plate by gravity, and that takes 20 minutes or so, maybe a little more, maybe a little less. We'll optimize that with users once we install a washer. And once the cells are settled, the action of dispensing and aspiration above them doesn't disturb the cells. So the wash solution forms a laminar flow, and it minimizes the turbulence of liquid flowing over the cells. And when you get close to the cells, the velocity of the fluid becomes 0, and then the diffusion takes effect there and washes away any unbound antibody. So interestingly, when we perform identical dispensing and aspiration with our washer using a conventional plate with walls, the aspiration and dispensing causes turbulence, and that'll lift the cells up, and that doesn't happen with the special plate that we have. So in the next couple of slides, and I'm just about done, and I'll turn it over to Prabhakar, I just wanted to quickly highlight some data we've run with collaborators and customers, and it'll complement the data that Prabhakar will present. So this first example is a rapid and complete washing of a stimulant to study the activation of T cells more accurately, without any artifacts coming from the remaining residual stimulant. And so in this case, we're comparing washing with the standard centrifugation method on the bottom and then DA cell on the top. And so in this case, IL-7 was added to T cells, and activation was monitored by pStat5 staining. So as you can see on the top, the DA cell washed cells in the top frames return nearly to a non-stimulated state faster than the centrifuge-based washing of cells, indicating that the IL-7 was washed away more completely in this case. So the next couple of examples I'm going to show optimized DA cell methods. So every time we work with a customer, we optimize their specific protocols. Now on this slide, I'm showing how the method can retain more cells, particularly from tissue samples, and the flow rate of dispensing and aspiration can be optimized as we've done here. So in this case, we've got 2 different flow rates shown with the maroon and gray checkered bars, and then in the tube with the standard method. You can see this is a relative to the tube. So the tube retention is 1, so 100%, and then with the DA cell, we're getting almost 2-fold, say with DAPI, and then over 4-fold with CD8 alpha. And then here, this also shows enhanced retention with tumor infiltrating lymphocytes, or TILs. And again, this is a relative expression compared to the tube method. So not as dramatic as the last case. Again, this is a ratio. So we see the tube method at 1.0, and then the DA cell method at a flow rate of 5 microliters per second. So we slowed it down a little bit to capture these slightly harder to work with cells. but still the retention ratio is higher than with the tube method. And finally, I just wanted to talk briefly about reading a plate on the flow cytometer. So I didn't mention it during the previous slides, but the DA cell plate holds up to 70 microliters, and that's great for washing most assays, but it might be too small to read on certain flow cytometers. So it depends on the flow cytometer, and often, say for example, a BD flow cytometer may require 100 to 150 microliters, depending on the functions of how the flow cytometer aspirates and dispenses liquid to mix up the cells and then draw them up into the flow system. So we do have an accessory to increase the volume of the plate when it's time to read, or if your particular protocol just can't be changed. Now, in this case, it's on an HTS plate reader on a BD flow cytometer. So the graph on the left shows the comparison between a conventional U-bottom plate and a drop array plate. And again, the drop array plate's in the maroon color, and the gray bars are the U-bottom plate. And as the graph shows, the reading from a drop array plate is as good as reading from a standard U-bottom plate. So even when the cell numbers are as low as 10,000, the recovery of cells by direct reading are comparable between a U-bottom plate and a drop array plate. So this concludes my portion of today's webinar, and with just a few highlights of customer data. And any questions you may have about the DA cell washer, please type them in and we'll answer them at the end. And right now, I'm going to turn it over to Prabhakar.
Good morning, everybody. This is Prabhakar Putheti. Friends in the HLA field call me with the short name Dr. PRA, the first three letters of my first name. So let's jump into the webinar. The title of my webinar today is Integrating Centrifuge Independent and Time-Efficient Automated Washing in Flow Cytometry Cross-Matching. So you would see on the top right, that's the slide number. And in case you have any question regarding any particular slide, at the end, you can indicate that slide number and I can go back and show that data and describe it or address any questions. There are challenges in flow cytometry cross-match technique, and the current challenges are as follows. Biohazardous flicking in plate method. If you're using a tube method for tagging, you may not be at health risk, but those that use plate method for tagging and flick their plates to remove supernatant get exposed to aerosols. Technologists should use face masks while flicking their plates into biohazardous containers or into the sinks. With cumbersome washing steps, there is room for error with the number of washes. So after the serum incubation, when you are centrifuging the tubes or plates for 3 washes or 4 washes, there's room for mistaking and doing less washes or more washes. I may be at wash 2, but I may be thinking I'm at wash 3 because somebody distracted me at wash 2. So less washes will cause incomplete washing, leaving unbound serum IgG in residual volume and preventing anti-IgG fixity from binding cell-bound IgG. If your positive control fails in your test, this is probably one reason. Residual volume from inconsistent flicking may affect your results too. A residual volume can dilute your serum and also your antibody cocktail. If somebody is pouring off, somebody may be pouring it off and holding it for some time, whereas somebody else would just pour off. So there will be a difference of anywhere from 10 to 30 microliters in a fax tube. Similarly, in a plate also, you would see that kind of difference. Finally, tech-to-tech variability. A well-built male tech may flick the plate harder than an average male or a female tech. And this can lead to difference in residual volume. Flicking harder removes more supernatant than flicking gently. In addition, cells exposed to hard centrifugation steps may affect flow cytometry results. There is literature on general flow cytometry regarding this, but we do not know if that applies to flow cytometry cross-matching. So this is how a Curiox instrument, the DA array cell washer and the plates look like. So you could see the Curiox instrument here and the plate, and this is the plate with the 70 to 80 microliter of the cell suspension or the media. So initially, when I add my 70 to 80 microliters of my cells, it looks like this as a droplet. So this instrument will have one inlet where you will have your wash buffer, your flow cytometry wash buffer, whatever you prepare in your lab. This is not provided by the company. So this is your wash buffer that you prepare. There's an inlet that goes into this instrument, and this instrument takes wash buffer from there. And after the wash is done, it passes on to the waste tank. So there is one outlet. So there are only these two tubings for the instrument. And you would see that these wells do not have a wall, but they have satellite wells. And you would have two nozzles in this instrument. For each well, one nozzle goes into one satellite well and the other nozzle goes into a second satellite well. And this works on a laminar flow process where your wash buffer would come from one side and is dispensed here. At the same time, your wash buffer is aspirated out from here, taking all the unbound serum antibody, unbound serum, and the unbound antibodies from your antibody cocktail. So this is how the washing process works. So cells are mixed with serum or antibody cocktail. While incubating through gravitation, these cells will settle down. So in your incubation process, the cells will all interact with your antibody as well as they're also settling down. And when the plate is put into the instrument by laminar flow, the wash process happens. One centrifugation wash is not equal to one wash of Curiox instrument. As cells should not be disturbed, it's a gentle wash. So you need to do 7 wash steps in case you're going to do 2 or 3 centrifugations for your washes in your regular flow cytometry. So because it is gentler, the wash buffer would come from here and it would just go over the cells. It's not very harsh as it happens in the centrifugation, but the process is so fast that the washing of 7 to 9 steps of wash steps is so fast that by the time I add my wash buffer from a reservoir into my plate first column, I change the tips and I take this multi-channel pipette tips, and again I take wash buffer and I go to second column. By the time I go to 3 to 4 columns, my DSL washer has completed 7 to 9 steps of washing. So this is pretty quick in case you're looking to save time in your flow cross matching. Washing steps through this method saves a lot of your time. I will show you our IGT method, Immunogenetics and Transplantation Laboratory. So our IGT method is here, and I will show you where the difference comes when you're using a Curiox instrument. So this is our lab-developed protocol. I developed this protocol based on my research protocols while I was working at Harvard. I joined this Immunogenetics lab in 2012 and switched the lab's tube method of tagging to plate method. My cells here, they are peripheral blood mononuclear cells or lymph node or spleen cells, and they are not treated by pronase. And I did not use any MESF beads, and I used plain mononuclear cells of the leukocytes. I did not specifically isolate lymphocytes for my flow cross matches. So I had 300,000 cells. They are dispensed in McCoy's media with 2.5% FPS. So I add 100 microliters of my cells in each well of my 96 well V-bottom plates, and then I centrifuge it, and I flick it and I remove the supernatant, so I have my cell pellet, and to that I add my negative control serum or positive control serum or test serum of 30 microliters. So this is my initial step. But when it comes to a DA cell washer, what you have to know is that the cells have to settle down. When you're adding this plate will only take 70 microliters of volume, 70 to 80 microliters you can add. And so it will take some 20 to 30 minutes for the cells to settle down. So initially it will take time. So what I do is, the first thing I do is that I add my cells to the DSL plate. And that is when I go and bring my sera. For the sera, I centrifuge it. And the time by the time my sera are ready to be added, the cells have settled down in the DA cell plate. To avoid this 20 minutes of waiting, I also did few experiments where I concentrated my cells 5 times. So basically here I had 300,000 cells in 100 microliters. I had concentrated so that I had 300,000 cells in 20 microliters. So I added 20 microliters straight to my well, to my DSL plate, and I added the negative control, positive control, or test sera, and mixed right away. So that would save your initial 30 minutes of waiting, 20 to 30 minutes of waiting. But if that is something that you would like to do, that is one optimization that you could work on. And here, this is one centrifugation that I would do 2000 RPM for 1 minute, whereas it would be 5 wash steps by Curiox instrument, but it is still faster than completing a centrifugation. And now after you add your serum, what I do is, in our protocol, we incubate at room temperature for 20 minutes, and then we wash it twice on the centrifuge with a wash buffer. And it's the same wash buffer we would be using here. And the incubation time is also same. But at the time of washing, I do a 9-step wash with Curiox instrument. Antibody cocktail addition is the same. Incubation 4 degrees for 30 minutes. That's what I do. And this 20 minutes and this 30 minutes is something where the cells will settle down in your DSL plate. So there is no time wastage that is going to happen because you're allowing the cells to settle down. So I wash it once at the end. Here it's a 9. This is still a 9 wash step by Curiox. And I add fixative and I run on my instrument, on my flow cytometry instrument, which is a PAC-Scan 2 instrument that I'm using. My T cell channel shift cutoff is more than or equal to 40 channels, and for B cell it is more than or equal to 50 channels. I have done extensive testings on the Curiox DSL washer. These are some of the following tests that I had performed. Parallel test between DSLs and our IGT method, an intraplate assay where I run the same plate, same sample in duplicates, and then I see the consistency. So same sample is run in duplicate in a plate of DSL, and I see how close the values are in the duplicates. So that's my intraplate assay. And when I do interplate assay, where I run the sample in 2 DSL plates, and I see the consistency between plate to plate. So that is my interplate assay testings that I had performed. And finally, which is very critical, is the tech-to-tech variability testing. I do not have a sufficient time to present all the data here, but I will show you a couple of interesting testings that would also be interesting to you, I hope. So these are the modifications I had to do to the testing to suit my lab results. Please note that these modifications may or may not be needed for your testing. Your lab protocol may be different, so you can see how this would fit in. One is the cell count. So as 70 microliters is a maximum per well in DSL plate, so only 210,000 cells per well were used. Although in my IGT method, I use regularly 300,000 cells. So I just still concentrated in the same way, regularly 3 million cells per ml. And I took 70 microliters for my DSL plate. And for my parallel comparison, I also used the 70 microliters, just 210,000 cells per well that I have used. And coming to GOAT anti-human IgG FITC concentration, this had to be 10 times more for DSL plate. So DSL plate received 1 to 20 dilution of anti-IgG FITC, whereas IGT method, in my regular method, I used 1 to 200 dilution. Large surface area of the drop and flat bottom in DA plate were versus smaller surface area and V bottom plate in my IGT method were the things that was making a difference. So this is something you need to titrate and see what concentration will suit your results. If you're using mouse anti-human IgG, God bless you. You may not need these titrations. I have got, while using GOAT anti-human IgG, I have got results with 1 to 30 dilution also, but I'm going to do further titrations because I don't want to use higher concentrations of GOAT anti-human IgG because I have seen that using higher concentration, it will cause non-specific binding and you will have very high MCF values. And there is residual volume of 15 to 20 microliter in the well after your washes are done. When you see, there's still 15 to 20 microliters equally in all the wells of the plate still remain. To reduce residual volume manually or using a wicking tool, residual volume can be removed by aspiration from satellite wells. Labs may optimize the test without removing the residual volume for easier workflow. I took a cell sample and treated with negative control serum in triplicate. I'll show you the data for my optimization. So this is where I took, I'm showing you the results of B-cell flow cytometry cross-match. Here I took a cell sample, and this was run in triplicate by IGT method and also by DSL method. So I had done it on my 96 well plate, the V bottom plate, and the DSL plate. I did the negative control serum. So these are median channel fluorescence. I'm showing you the data of negative control and the positive control, IGT method, DSL method, IGT method, DSL method. And result 1, 2, 3 are the triplicates. So when I say result 1, it is one of the 3 triplicates of the same sample. I'm only showing you data of one cell here. So if you see for the IGT method, the MCF values, this is 1024 channel scale that these results correspond to on PAX Viva for PAX Cantor 2 instrument. So 216, 214, and 220 were the triplicate MCF values by IGT, whereas 379, 382, 383 were for the DSL. You would see that the MCF values are higher. This method is more sensitive, where the antibodies and your serum are binding very well to your cells, and they are neatly washed off. So when coming to positive control serum, it is 427, 390, and 398 of my triplicate. This is in the same plate. And whereas for the DSL, it is 567, 558, and 561. So as you know, the channel shift is the MCF of your positive control or your test serum, where your negative control is subtracted from your test serum positive control MCF values. So 390 minus 214 for IGT method had given me 176 channel shift, whereas 558 minus 382 had also given me 176 channel shift. Coming to these values, 398 minus 220, 561 minus 383 had given 178 channel shift. So what I'm trying to show you is although the MCF values are higher with your DSL method, the channel shifts are similar. So the increase is constant. So maybe if you titrate it further, and if you are suspecting, in your case, if you're suspecting higher background with your goat anti-human IgG concentration, you need to titrate it further. Maybe that would bring down your MCF values. So you need to clearly check what concentration will suit your protocol. So these are the standard deviations, and these are the means. And the intra-assay % CV for IGT method when it comes to negative control is 1.4, whereas DSL is 0.5, and positive control is 4.8, and DSL is 0.8. So inter-assay is 1% for B cells with negative control and 2.8% for B cells with positive control. This is pretty good, because for inter-assay, I'd put a threshold of 10%. It should be less than 10% CV. And this is a very good % CV that I have noticed. Now I'm showing you T-cell flow cytometry cross-match for the same cell. The results are put in the same way: negative control, positive control. These are the triplicates. And if you see the values, so 182, 178, 183, 232, 239, 241. Actually, with your negative control, the values will remain pretty close. But when you look at the positive control, that is where you will notice the differences. So here, in case of IGT, is 272, 251, 256, still good. And DSL is 361, 364, 358. They are pretty close when it comes to DSL. So intra-assay % CV is 1.5 and 2 for IGT DA method, 4.2 and 0.8 for positive control IGT and DA method. Here you would see that for negative control T cell, the IGT method showed a better intra-assay percent CV, but they are close. Inter-assay is 1.7 for actually, I'm sorry, these are for T cells, and this is 2.5. Now, the results here say that the intra-assay percent CV was less than 5%, and inter-assay percent CV was less than 3%. This suggests good consistency for both the test methods. So I had shown you the data, so this is reiterating the same thing. So now I'll show you tech-to-tech variability. So here what I did was I called 3 technologists to perform this test side by side with our IGT method and DSL method. Each tech performed the test on 1 cell in duplicate, on IGT method, and on DA plate. So one tech had worked with 2 plates. One is IGT plate and one is DSL plate, and it was only 1 cell. And the test included cells treated with negative control serum and positive control serum. So I'm only showing you negative and positive control sera in these testings that I have shown you so far. And the 3 techs worked side by side with their own plates. So this happened at the same time. So they were all working side by side. It's not that one did in the morning, one afternoon, one in the evening. So there is no time variability here. Total, there were 3 IGT plates and 3 DSL plates. The percent CV is the standard deviation divided by your average multiplied by 100. And the DA concentration that I used here for the DSL plate, the FIT-C concentration was 1 to 30 dilution. I'm showing you B-cell flow cytometry cross-match results. So this is negative control results, and these are positive control results. This is IGT, this is DSL. Result 1, result 2 would mean this is a duplicate. And the results of tech 1, and this is tech 2, and tech 3 are like this. So if you see for negative control, again, the values are close for IGT method as well as for the DSL method. They are very close. Now, if we focus on the positive control, it's 480, 433, 485 for the 3 techs. Whereas when it, then these are the duplicates, 455, 422, 498. So there is little variability, but they are still good. When it comes to DSL method, the values are even closer with 651, 627, 653 for the 3 techs, 626, 641, 619 for the 3 techs. If you see the percent series, 1.3 and 2.3 for IGT method, 1.5.8 for DSL method. So these are the duplicates actually. And for positive control is 6.2 and 8.3 for the IGT method, and 2.2 and 1.6 for the DSL method. So tech-to-tech variability, negative control is 1.8, 1.1 for IGT and DA. The percent CV, and positive control is 7.2 and 2. And in the inter-assay between the IGT and the DA, I would take an average of this, and it would be 1.4 and 4.6. So as you could see, this is the B-cell results, and now I'll show you T-cell results. If we straight away go to positive control, because negative control values are still the same. See here, they're so close, they're identical. For the positive control, 344, 316, and 357, whereas result 2 is 327, 309, 364. And for the DSL method, it is 493, 474, 494, and result 2 is 453, 489, and 449. So the percent CVs are 6.2, 8.4 for IGT method, 2.3, 4.8 for the DSL method. So they are still the inter-assay between the IGT and DA. They are still less than 5% for negative control, and positive control is 5.4%. So to conclude, what we could say is that the Curiox DSL instrument is a great time saver. It's an easy workflow. And if you had a tabletop incubator and refrigerator, you can sit at your bench and complete the tagging without getting up. You could just find an article to read during your incubation steps. It's safer as there is no biohazardous flicking, and there's better tech-to-tech consistency. And techs still need to mix the cells and serum or cell and antibodies. So this variability is beyond Curiox instrument. It is mainly for washing of your cells. If you have to take the residual volume off manually with pipette, that will add a tech-to-tech variability. So I would suggest to optimize your method where you do not remove residual volume. And these plates are not made for centrifugation. If you're thinking that you could centrifuge and you can flick these plates are not made for that. So avoid doing that. So I would suggest to optimize your method accordingly. And regarding IgG FITC, the titrated concentration is very crucial. Using high concentration of your goat anti-human IgG FITC, it will cause very high background. So you have to optimize and use as diluted as possible to get proper results. So thank you very much. And I'm ready to take your questions if you have any.
Wonderful. Thank you, Dr. Putheti. That was a very informative presentation. And we do have some questions that have come in. First one, how easy was it to use the plate and washer? A plate does not have any walls separating the wells from each other. Did you see any cross-contamination?
I did not see any cross-contamination. You should still be careful while transferring your plate into the incubator and bringing it out and putting it into the washer. Not because they would cross-contaminate. It never happened that one droplet went into other droplet, because they're still separated on the plate. If you see there's a crevice, these drops, they do not wander around. My only concern always had been not to disturb my sedimented cells because you want them to settle down. If you shake them too hard and then you put it in the washer, you are going to have your cells aspirated out and you will have very less cell count.
Thank you. How fast and easy was it to optimize the assay? Specifically, how many days of work did it take to achieve the right assay conditions?
This would vary, I believe, definitely. No, not believe. It's definitely, it will vary from lab to lab depending upon your protocol. Because I was the first one to use this instrument for my flow cross matching. There were lots of testings that had to be done in terms of, I did not know that residual volume was affecting my protocol. So that I identified after 3 testings. And I did not know that the concentration, I couldn't use 1 to 200 in this because of the droplet, the higher surface area, your secondary antibody becomes unavailable to bind to your cells. So there is some secondary antibody that will become unavailable. So that's the right way to put it. So that was not something I knew before, because I had done all this groundwork and I had presented it here. So I think this would save time for your optimization, but I don't think it should take much time, because at the end of the day, it is a washer. It is washing your cells and giving it back to you.
Okay. The improvement of the CV by DA cell from tech to tech variability sounds great, but does it really matter, as your manual reproducibility looks good enough?
My manual reproducibility is good enough. The reason is that I wanted to, my first concern was the biohazardous flicking. I did not like that part, where I would ask staff to use face masks, and it's very difficult to wear a face mask can work. So I was always a little afraid about that techs would get exposed to these aerosols, and these patients have HIV and all kinds of hepatitis infections, and you don't know what's happening in the patient. So it's very important to be very careful with this, and that flicking part I did not like. And yes, my method gives consistency. As you could see, there was somewhere around 5 to 8% probably a variability between the techs for the positive control. But getting it even lower and low percent CV is always good. And mainly it's an easy workflow. You would really love it. I think if it works in your hand and with your protocol, you would see that how easy it is. You don't even have to get up from your bench to go walk to the centrifuge.
Good, thank you. The Curiox portion of the presentation pointed out that they are developing a fully automated workstation. Are you planning to automate the entire workflow?
As I showed you, one of the variability would be that you're still adding your serum to the cells and mixing it. And that mixing part is one variable that could show differences between the techs, because I had seen some of the techs who would add 30 microliters, but they would press the pipette all the way down and it releases air into the well, and then they aspirate all the way up. They will take the whole thing. Now, instead of 30 microliters, you're getting 50 microliters, and there isn't 50 microliters in a well. So you're getting air. And by the end of this mixing, they generate so much of air bubbles that there's a froth actually. I don't know how long these air bubbles will take to burst out and the antibody becomes available. I don't know if cells could be sticking to the well, to the walls of the wells in the plate, regular methods. So there is room for variability there while you're adding and you're mixing. But and in case you're trying to remove the residual volume manually, there's room for variability there also. So I think you have to be it's better to automate the whole system of mixing also, but you could see how much these variabilities are going to affect your results. If the washing is uniform, I think that solves half of the problems in flow cross matching.
Next question, what is the residual volume left in the well after the DA wash?
I had seen 15 to 20 microliters. So when I had manually taken the liquid out with my pipette, I saw somewhere around 15 microliters coming. So that is there. That kind of residual volume is still there. But does it affect your cross-match protocol for your antibodies and for your concentration? That may differ from your protocol to my protocol. But I would suggest that have a protocol where you don't have to remove the residual volume.
Okay, next question. Is there ever a problem mechanically where the probes of the instrument don't align with the nodes at the edges of the well? And if so, how often?
That had been my biggest fear initially, because there are so many nozzles there, 96 into 2. So I was always concerned that there could be a clog, and I wouldn't know that maybe in the middle of the wash this clog would happen, and I wouldn't know. But that doesn't happen. It's not individual nozzle-wise washing. As I see, the whole I don't know how to put it in words, but whole liquid is pushed at once into all the nozzles, and it is taken off. It's aspirated all at once. So it's not different tubings going to each of the nozzles, as I believe that's how it is. But initially, every day before you start your run, what you do is when you're calibrating your plate, you will add it. When you press that button for calibration, it is going to dispense a volume. I think it is 80 microliters of volume, and you see this as a droplet in all your 96 wells. And then you place it in, and then it does the washing, and it removes the liquid, and it gives the plate back out, and you will see that all the 96 wells, the droplet has gone. So that is an indication that your instrument is working well on that day for you. And in case it is at that time, if you see there are some wells where there's still a droplet sitting there, it had happened sometimes. For that, you will have to do some kind of maintenance, which is very easy. I could do it myself, but it rarely happens. If at all that happens, you could do it, or you call tech support. And with Curiox, I had a few this tech support individuals who would come right away and take care of it and perform complete maintenance. But no, it's not a clogging that would happen. I had used HTS system on Fax Canto too. It's not that kind of clogging, that kind of fluidics issue that you would face in Curiox, a DSL washer for this instrument. I hadn't seen any issues.
Great. Next question, when adding staining antibody to the DA plate, do you mix by pipetting, dental vortexing?
The instrument comes with a vortex, and I did do vortexing. I placed my plate on that, and that wasn't sufficient for my mixing. I had to mix with pipette. I did mix it with pipette, and after that, I vortex it. That is fine, but just vortex is not sufficient enough. It's a very good question. This would save a couple of experiments for you, because I faced some failed experiments because of just relying on vortex and not mixing it. You have to mix it manually with your pipette before you put it for the vortex.
Next question, have you used larger volume plate insert?
Larger volume plate insert, I did not use. The DAS, Curiox has it, which they're testing it for single antigen bead assays. They have some kind of inserts for that, but I haven't used it for flow cross matching. That's an interesting thing. Maybe I should test that, but I haven't used it.
Okay, next question. Why are B negative values 150 to 200 channel higher with DA?
Why are they higher? But if you had seen those slides where I had shown channel shifts, the channel shifts are similar as compared to my IGT method. Overall, the MCF values are higher with my negative control and positive control, but I did not see a difference in channel shift. So I think that is not a problem. It is not, if you're thinking it's a non-specific binding that is happening and it is showing higher channel shift, that is not what it is happening here. So one doesn't have to be feared about that. But again, in case you're using higher concentration of IgG FITC, you have to be very careful.
Okay, and our last question, are you using ACD samples? Have you tried the Curiox system with heparin or EDTA samples?
No, I did not. I am using ACD sample. That's a great question. I'm using a ACD sample, and these are peripheral blood mononucleuses that are isolated, and I'm using those ones. I'd also used spleen cells and all, but no, I did not use heparinized blood for the cell preparations for this.
Wonderful. Well, thank you so much, Dr. Putheti, and everyone, thank you for attending. If you have any questions, please send us an email at sales@curiox.com. That's sales@curiox.com. Thank you, everyone.